Yeah, welcome, welcome. I can see two people already there. Welcome, my students. Today we are revising with BCHD and BMLS regular. Welcome all, welcome. We are revising carbohydrates. Hello, Tabitha. Hello, welcome. Anybody can join, even BMLS upgrading, but we are having BCHD. Hello, welcome everyone. Just do the charts, BCHD, BMLS, BMLS upgrading, BMLS regular. Any student who is on board, who is live now, just let me know in the chat so that I can welcome you all. Tabitha, welcome. Yeah, let's keep on logging in because we have a lot to revise on. So, Mohammed, wow, Abdi Aziz, BCHD, welcome, welcome, Mohammed. Welcome. We encourage all students to stay tuned. Mohammed, I hope you got the revision questions. Yeah, Odero Millicent, BMLS app. Welcome, Millicent. Welcome. Thank you all, students. Let's keep on logging in. Good. From Susan. Hello, Susan BCH. Yes, welcome, my dear. Harriet Kalmoy, BMLS. Yeah, BMLS, upgrading or regular? Harriet, tell me. If it's regular, I welcome you. Upgrading, I welcome you. Assalamu alaikum, Brian Akesh. Alaikum salam. Rita, BMLS app. Welcome, welcome, my dear. Welcome you all. Let's keep on logging in. BCHD and BMLS regular. Together with BMLS upgrading, I welcome you all. We need to do revisions. The BCHD are going to have their cuts and the BMLS regular. Oh, good. Harriet, thank you so much. Welcome, welcome. Let's keep on logging in. We'll give 5 minutes so that we can start by 9:10. But I always wait for the class reps. Yes, Smart, Dabos, welcome, welcome, my dear. Welcome all. I always ask for the class rep. The class representatives for the three groups, the BCHD, all the years, the 2023, 2025, 2024, and then the BMLS regular. If the class reps are there, please just let me know so that I can see you are also well represented. But then we shall start at exactly 9:10 so that we can have time to revise all those questions because we still have the cut on Friday. However, I heard the BCHD are going for a trip, but then the group which is going for a trip, that's how it works. So I'm not going to cancel my cut. The cut is going to be on Friday. For the ones who are going to be there are going to do it. But I need a communication from the HOD. Dr. Mushiri has to communicate to my email the students who are going for that trip. If you are not going, you have to come and sit for the cut. If you are going, I'll follow the list and I'll give a makeup cut at the end of the semester. So I'm not going to cancel the cut. The class rep told me the BCHD group are going for a trip. So possibly some of them will not be in for Friday, but we can't cancel our cut. Our cut still remains. But I need an email with a list of the students. So I don't always give makeups that easily. So when giving the makeup, I'll follow the list which has been submitted by the HOD to my email before you go for the trip. So our cut will not be cancelled. If you don't, your name do not appear in the list which the HOD will send to me, because I'll also consult the HOD. If your name will not appear in that list, I'm not going to give you a makeup cut. It means you're supposed to be there for the cut on Friday. So our cut still stands and we are going to revise. Let me keep on welcoming the ones who are there. Oh, I was still at Smart. Welcome. Please stay tuned. We are almost starting. I think I give 2 minutes. I'm going to start. So the BMLS, the class rep, I sent to the students. Smart, did you get the revision questions? I even sent to BMLS app. And Rita, I sent to Felix. Daisy Ochieng, welcome, Daisy. Just tell me if you got the revision questions, because I'm going to start and we are going to follow those questions the way I had put them. Whatever you can see there is the board. We are trying to manage with whatever we have. So I encourage the students to keep on logging. We are supposed to start. If I start, then they'll be able to come in. So it's okay, because I'm going to start in a minute time. So I'm giving 1 minute so that the students can come on board. Oh, good. Smart tells me they got it. Thank you so much. Thank you so much for the response. I need to start. Then the other people will come and join, because we can't wait for the others to join for like 30 minutes. That will be too much. So let us start, and then they'll join us as we proceed. Because remember, we have to cover carbohydrates. We have to cover amino acids. We have to cover water and buffers. So it's a lot. So if we assume that we still have enough time, and it's already at night, I always like staying for 1 hour. But sometimes if I have to finish the revision questions, then it might take longer than 1 hour, because you also have to ask for the questions. It's okay. Oh, Masjid, Rahma, yes. Welcome, my dear. So the topic of discussion, your BMS. So today, okay, any student can join, but the BCHD group and the BMLS regular, they are going to have their cut on Friday, this coming week. And as I promised, after every topic, I always do revision with the students so that they can know how to answer a question when they sit in the cut or the main exam. So the main issue here is after every topic, I do revision. So today I'm doing revision on water, buffer. Water, I'm not going to discuss the characteristics of water because that is obvious. We are going to derive the pH of water as 7. I'm explaining to Majid. We are going to derive the Henderson-Hasselbalch equation. We might also discuss the equation where water is a buffer. And then after that, I'm going to discuss sample questions which are found in carbohydrates. And since I've also covered the structures of 20 amino acids and a peptide bond, I'm also going to cover that. Then I'll stop. Majid? Did I explain myself? So you can also stay on board. It doesn't stop any student from joining. Any student can join because you can pick something or even ask questions on the chats, and I'll be able to do that. So Majid, ours is not today. The cell biology will do it on 20. Was it on 17th? 15th, something like that. One of the Saturdays before we have our exam, our cut. So it's okay. You can still join. Yeah, thank you so much. I can see you responded. So we are going to start. Any of the class reps on board? BMLS app, fellow, maybe you are somewhere, and I hope maybe you are planning to join because I've seen my BMLS app. And then we have BMLS regular. We have the class rep who I always communicate to, BCHD. I don't know her name. But if you people are there, we are going to start, please. And I always ask for permission from the class rep. But since we have 4 class reps in that class, I'm just going to start so that we can join. I think even the members who are there, you also have a say. You can agree with us. We just start. And then as we proceed, they are going to join. So let me open my question, my PDF. which are the questions, and then we can proceed without wasting any time. And let them keep on joining. Let me just check, and then I can proceed. As they logging in, but then I can start. I can start. Class reps, are you there? Dorisian, yes. Hi. Doris, tell me the BCHD class rep whom I always communicate to. If you know her by name, you can tell me the name so that I ask if she's already there. Whoever didn't get the questions, kindly just share with them so that nobody's left out. Nobody is left out. So I'm going to start with the carbohydrates first. I'm going to start with the carbohydrates first, and then the last bit is for the amino acids, just the way we've been having our lectures. But then the buffers and water will always come. Oh, Tabitha. Thank you, Doris. Tabitha, are you there? I'm starting already. Without asking permission, then you'll be able to join. Huh? So they'll find us as we proceed, but then they can go to the charts and ask if a structure is not clear. If something is not clear, you are allowed to ask, as long as it relates to whatever we are doing. So we are going to start with the questions. I'm just opening and we are almost starting. So you just follow the questions as I sent them. We are going to start with question number 1. That's how we are going to go until the last one. So as I said earlier, there are a bit too many, so we can't assume that we'll take shortest time possible. But what I'm interested much is the students should understand. Oh yes, Tabitha. Good, you are there. Tabitha Chepkemoy. Thank you. Hi. Please just confirm if the other class reps are there. Medical lab, I haven't seen the class rep. Class rep medical lab regular. Maybe the other guys for BMLS can tell me the name. Then he confirms if he's there. But I must say that I have to start now. Question number 1 says, yes, Steven Santino. Hi, are you the class rep? Class rep medical lab? Oh, it's okay. I can see everyone is represented. Please, we're already starting. Check if you have your neighbor where you can share the questions. We're already starting without wasting any time because we need to cover. Tabitha, I don't know whether you heard what I said, but I said that the cut still stands on Friday. What I need from your end is the list from the HOD. It has to be sent to my mail. It has to be sent to my email. The HOD himself, Dr. Mushiri, has to send the list of the people who are going for the trip, because those are the people I'm going to give a makeup. If the name do not appear there, I'm not going to give a makeup. So we are not canceling our cut. We are going to do a cut. Whoever is going to be available will do the cut. Whoever will not be there and the name will not appear in the list from the HOD's desk will not do a cut, even if it's a makeup. Only the ones whom their list, the name appear in the list will do the cut. So I'll give a makeup cut at the end of the semester. But for now, our cut still stands on 7th, as we discussed earlier. Nothing is changed. So we'll be able to discuss further. Thank you so much. So you'll just go to the HOD's office on Monday, and then you can convey the message, but I'll also do an email. So that one is set. We are starting. Define the following and draw structures to support your definitions. I'm saying 1 mark each. You define and give structures. We are talking about stereoisomers. You define by saying. If they are exoses, they are of the same molecular formula. C6H12O6. If they are trioses, they'll be C3H6O3. So they have the same molecular formula. Also, even the functional, they're the same. Functional group is the same. But there is a difference in structure. But the difference in structure comes as a result of their mirror images of one another. So the stereoisomers are mirror image of one another. So if you talk about stereoisomers, after that simple definition, most will go for the structure. So whatever we are talking about is you have glucose, D-glucose to be precise. 1, 2, 3, 4, 5, and then the sixth one. We said for D-glucose, you will go to carbon atom number 3, OH to the left. Whenever there is an OH to the left, the hydrogen is right. We are talking about water as an ideal biological solvent. At carbon atom number 2, number 4, and number 5, put the OH to the right. That is D-glucose. So we are talking about D-glucose. 6 carbons down the line, 1, 2, 3, 4, 5, and then the sixth one. The sixth one will be CH2OH. Carbon atom number 1 will have the aldehyde group. At carbon atom number 3, we are drawing D-glucose. OH is to the left. Put the hydrogen to the right. Carbon atom number 2, 4 and number 5, put the OH to the right, put the hydrogen to the left. It means for L-glucose, you will still have the 6 carbon atoms, 1, 2, 3, 4, 5, and then the sixth one, still the same thing. At carbon atom number 1, you have the aldehyde group, but now you are drawing L-glucose, go straight to carbon atom number 3, put the OH to the right, then bring hydrogen the other side, still characteristic of water as an ideal biological solvent. Now, at carbon atom number 2, number 4, and number 5, bring the OH to the left and then the hydrogen to the right. And those two are stereoisomers. Very clear. I just came to check. Yes, David. Hi, my dear. We already started. And I have to check if everything is fine. So I'll be able to rub my board as we proceed because it can't focus the whole board. But that little space which we can utilize, it shall be well. So look at the structures of D-glucose and L-glucose. It talks about stereoisomers. Same molecular formula. Since they are exoses, you can talk about C6H12O6. But if you look at their structures, they are mirror images. So you don't interfere with carbon atom number 1, neither do you interfere with carbon atom number 6. You only interchange the OHs and Hs from carbon atom number 2 to carbon atom number 5. It means even for the trioses, very simple. The best example I've drawn here is known as glyceraldehyde. And this one, you will be able to talk about. L-glyceraldehyde. This is D. This is L. That's how simple it is. So the stereoisomers, they are mirror images. Whatever was to the right comes to the left, whatever was to the left comes to the right. That's how simple it is. So even the ketoses will have the stereoisomers, mirror image. So you talk about the ketoses, Fructose, D-fructose, will look like this. The second carbon, keto group, at carbon atom number 3 for fructose, OH to the left. Fourth carbon atom, fifth, then the sixth one. It means that L will look like this. You don't interfere with carbon atom number 1, 2, and number 6. So it will look like this, it will look like this. That is L. We are talking about stereoisomers. Stereoisomers. 1, 2, 3, 4, 5. And then the sixth one. So we have D-fructose, and then that one is L-fructose. We are talking about stereoisomers. They are of the same functional group, same molecular formula. Yes, Kanda Talam, welcome. I have to welcome Mohammed Abdiaziz. Which part do you want me to repeat, my dear? The stereoisomers, I said. Keyboard, Vincent, hi. We are on board, already starting the revision. Anybody can join anytime. Abdi, you'll tell me what to repeat. I'll be able to repeat. That's why we are here. So I'm talking about stereoisomers. We are at question number 1. Mirror image of one another. I understand my MBCHB are talking about enantiomers. I said, if you can grab something which is the same, as long as, hi, Charity, welcome, as long as it is taught with different lecturers, but you can get the same concept. Moses Mumo, welcome. Hi, we are already starting on question number 1. I'm happy people are joining. Let's keep on joining. We are talking about stereoisomers. Yes, Jackie, hi. Meko Kam, hi. Everyone, I'll be able to welcome you. Please, don't worry. Feel at home. I'm talking about the first question. I didn't share with MBCHB. I'm sorry about that. I ignored. But I shared with BMLS upgrading, but I'll be able to mention the questions. We were on stereoisomers. Eunice Omondi, hi. So we are saying the stereoisomers, you can see on the board, I already drew of glucose. They're of the same molecular formula, if they're trioses, if they're tetroses, if they're pentoses, if they're hexoses. But at a certain point, if you look at their structures, they are mirror images of one another. So something which you've also noted is they're of the same functional group. If they're ketoses, they're ketoses. If they are aldoses, they are aldoses. Second question says functional isomers. Now, functional isomers is different. They are still of the same molecular formula, yes. For functional isomers, they can be all hexoses, they can be all trioses, they can all be pentoses, but the structure is different based on the difference in functional group. I repeat. We are on question number 2. Question number 1, Roman 2, sorry. Okay. Thank you, Stephen. Oh, the class rep is Ruth. No problem. Thank you. Now I'm saying functional isomers. Same molecular formula. But then the difference in structure is based much on the difference in functional group. So I'll leave the D-fructose there, and then I'll draw D-glucose to show we are talking about functional isomers. They are of the different functional group. If you look at their structure, one is a ketose and the other one is an aldose. So we are talking about fructose, and here is ketose. Those are functional isomers. And it has to be D. If it's D, it's D. If it's L, it's L. So you talk about D-fructose, D-glucose. 1, 2, 3, 4, 5. And then the sixth one, we are drawing D-glucose because this was D-fructose. So At carbon atom number 3, put the OH to the left. Put hydrogen the other side. It means at carbon atom number 2, number 4, and number 5, you will put to the right, and then still we are talking about the characteristic of water, ideal biological solvent. So you'll have something like that. So they are functional isomers. Eunice, fructose is a ketose. Fructose is a ketose, this one, keto. Aldose, this one is, glucose is an aldose. Fructose is a keto. Yes? Eunice, did you get that one right? Yes. Thank you. I'm happy about that. So the keto group at carbon atom number 2. The aldehyde group at carbon atom number 1. The difference in structure comes as a result of the difference in functional group. One is a ketose, the other one is aldose. So they are functional isomers. However, they are of the same molecular formula. They are both exoses, C6H12O6, but the structures, difference in structure clearly shows that they have different functional group. Epimass. You know epimass, we were talking about if a monosaccharide, there is a difference in a specific carbon atom, which is not the carbonyl-carbon. Carbonyl-carbon is a carbon which has the functional group, the one which carries the functional group. Then you call them epimass. So we are talking about epimass. They have to be both. If they are epimass, they have to be aldoses or they have to be ketoses. They have to be of the same functional group. They can't be different. So that's how they differ with functional isomers. So if we have the aldoses, it's aldoses. If we have the ketoses, it's ketoses. But then the epimers which we know are these ones. So I'll put our glucose in the middle so that I can highlight what epimers are. Let me do D-glucose, 1, 2, 3, 4, 5, 6. Here, I will draw galactose, 2, 3, 4, 5, 6. Here, I will draw mannose, 2, 3, 4, 5, and then the sixth one. So if you look at them, the first carbon has the aldehyde group. Let's go to the last carbon atom. For all of them, it will be CH2OH. So what you do here is, let's start by drawing the structure of D-glucose. 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 I'm highlighting the carbon atom number 3 in green, and then the other ones can remain the same to bring clearly the definition of epimass. At carbon atom number 4 and 3, for D-galactose, I'll highlight in green. The other ones can remain the way they are. The other ones can remain the way they are. For mannose, I'll highlight at carbon atom number 2 and number 3. I'll highlight in green so that the other ones can remain the way they are. So I'm talking about D-mannose. If it's this D, I'm talking about D-glucose and D-galactose. We are talking about epimass. They are of the same molecular formula, yes, we agree. Mannose is not visible. Yeah, I'm going to, Now, it has captured. Majid, do you see? I don't want to interfere with whatever has been put because sometimes the camera will bring a lot of problems and yes, we can see now. So we are there. Look at the functional group at carbon atom number 1. The functional group at carbon atom number 1 for D-galactose, the first monosaccharide, is an aldehyde group. Glucose, the main one, D-glucose, first carbon, aldehyde group. D-mannose is the one to the farthest, still at carbon atom number 1, aldehyde group. They are all hexoses, 6-carbon sugar, C6H12O6. Same functional group, they're all aldoses, but there is a change at a specific carbon atom, which is not the carbon atom number 1, which carries the functional group. So the reference point is glucose. That is why I've put glucose there in the middle, such that you can easily see that the difference of glucose and galactose is at carbon atom number 4. The difference of glucose and mannose is at carbon atom number 2. So you'll say that mannose is an epimer of glucose at carbon atom number 2. Remember, I said mannose is the epimer, not glucose being the epimer. That is where the students go wrong. Just by a change of a statement, everything is wrong. It doesn't make any meaning. Somebody says glucose is an epimer of mannose. No, it is mannose. You can see, if you look at the structures of all the 3, at carbon atom number 3, everything is the same for all the D. But the difference will only come on mannose and galactose. But at which carbon atom? At carbon atom number 2 for mannose. So mannose is an epimer of glucose at carbon atom number 2. To be specific, say D-mannose is an epimer of D-glucose at carbon atom number 2, while D-galactose is an epimer of D-glucose at carbon atom number 4. So if we talk about a pair, epimer pair, glucose has to be there. It is either glucose and mannose or glucose and galactose. As simple as that. I told you, don't cram to know a structure. I always say, and students will always finish my statement, you will see fire without smoke. Yes. It can be very dry until you wonder what happened. So just master. You just know the 6 carbon atoms, know the functional group, where to place is right. If you talk about the D of those monosaccharides, which one can you place where? Just try to understand how the structure come about. Roman number 4, pyranose. Simple as that. The resulting 6-membered ring is what is known as pyranose. It means the aldehyde or the aldoses. The OH at the 5th carbon atom, and I'm going to use the glucose, which is there on the board. I can also use galactose, so it's okay. Let me use galactose because we can see it clearly. We are talking about pyranose. When you talk about pyranose, the first thing which comes into your mind are the aldehydes, the aldoses. The OH, I'll use this one. This galactose, don't worry. I'll use this galactose. I'll use this one. We are talking about pyranose. I said that the OH at the 5th carbon atom and the first carbon having the aldehyde group, 1, 2, 3, 4, 5, 6, are going to form hemiacetal. So if you see the aldehyde group there, go straight and make the 6-membered ring. Put the 6-membered ring in place. Go straight. Put the 6-membered ring. If you see the aldehyde group, go straight. Put the 6-membered ring. But remember, here is the hemiacetal. This one has to be there. The covalent bond which is forming there. And then I said that in this case, we want to draw, whenever you see the cyclic form, it is either alpha or beta. So we add the one alpha, D-galactose. If you want to draw it, the OH at carbon atom number 1 will be below. It means that for this one, we are twisting in clockwise direction. At carbon atom number 2, you'll have the OH outside. At carbon atom number 3, inside. At carbon atom number 4, the same direction as carbon atom number 3. This is the hydrogen, this one. And then CH2OH. So for the pyranose, as long as you draw for me something like this, I can also give you a mark. Or if you decide to draw the alpha or beta, D-glucose or L-galactose, however much, it will not be even correct, but as long as you show me the 6-membered ring, I'll give you a mark. Tabitha, D-glucose and galactose differ only in configuration of the hydroxyl and hydrogen group at carbon atom number 4. OH group is the right side at carbon atom number 4, while in D-galactose, it is in the left side. Tabi, are you trying to, oh yes, start high. Are you clarifying the point of epimass, Tabi? We need to move together. D-glucose and galactose differ only in the configuration. Yes, yes, correct. So that was the epimer. Yeah, let me answer this first. Is that alpha or beta sign? That is alpha. Phoebe, that is alpha. You can see I added alpha in green so that we can draw alpha. And alpha, look at carbon atom number 1 of the cyclic form of those aldoses or of that D-glucose we are drawing. If it is below the ring at carbon atom number 1, if it is below the ring at carbon atom number 1, then we talk about alpha. You get, Phoebe? The beta, it will be above. You get, Phoebe? This is alpha. For beta, it will be above. That is a beta. It will be a beta D gal or D galactose. Moses is talking about, don't be worried about marks. Learn how to draw. Moses, leave the marks alone. Of course, those marks will not make sense. How can you get only 1 mark after explaining all this? It means I'll adjust it to fit to the question. You get? Don't be stressed of the marks. I want you to concentrate and understand the structure. The marks is a minor thing. That is very minor. Don't worry about the marks. It can't be 1 mark. You explain and you draw marks. You get? You draw structure. So possibly it can't be a minimum 2 marks. Moses, don't worry about marks, my dear. We need to get the point right. Good. Phoebe has understood. So we are moving. Hemiacetal already. No, there is furanose. Correct. Sorry. So we can cover hemiacetal as the time we are covering pyranose. The hemiacetal is this. So you'll have to draw for me still the cyclic form. In fact, here it shows well. That is hemiacetal. Hemiacetal, just by drawing it and pointing, you see that round thing there, it adds more marks. Twisting is a bit confusing. Good. Wait, let me go up first. The first person. Any explanation on carbon number 5? There, or Millicent. I say that carbon atom number 5, you can see the OH. For the aldoses, the OH at carbon atom number 5 is going to form a covalent bond with the carbon carrying the functional group. So that is where we have the hemiacetal for the aldoses. And that is what we defined. By the time we were writing notes in class, by the time we were projecting for my BMLS upgrading. So I'll be able to answer each one of them. Don't worry. Just tell me, then I'll be. Now I want to answer Glory before it goes up. The twisting is a bit confusing for Glory. Glory, we are going to twist now. Is that carbon atom number 1 the anomeric carbon? If yes, what is its correct definition? Let me answer Glory first. Of course, the anomeric carbon is the first carbon atom number 1 in the case of aldosis, which has the aldehyde group Majid. The ketosis will have the carbon atom number 2, where the keto group is. So we are talking about the anomeric carbon, the carbon which carries the functional group. Yes. So beta OH is top, correct. Alpha is below. Paranai is confirming. Now I want to make it for Glory easier to twist. Glory, I'm going to draw a clear one because we should move together. We are not going to leave somebody out that we have to finish. Glory, I want you to concentrate. And then I'm going to draw for fructose so that we can answer furanose and hemiketal. Glory, for your sake, let me do glucose, carbon atom number 1, which has the aldehyde group, 2, 3, 4, 5, and then the 6th one. Let me do L so that you can see how we are twisting. I want it to be a different one. At carbon atom number 3, we are drawing L, glucose first. So I told you that if somebody talks about L and D, that person wants you to draw in linear form. If somebody wants you to draw a linear, they'll be able to talk about L, glucose, L, fructose, D, mannose, D, galactose. You'll know. Go straight and draw the linear form. But immediately, somebody says, we talk about beta. Now this one, beta, L, glucose, beta. This one will tell you that this person wants you to draw in cyclic form. So, Glory, I'm repeating this one so that you can understand. For the aldoses at carbon atom number 1, there is an aldehyde group. You know, we said the pyranoses, they result, the 6-membered ring will result from the OH at the 5th carbon atom forming a covalent bond with the first carbon carrying the functional group. So they will result into a 6-membered ring, the aldoses. 6-membered ring, draw the 6-membered ring. And then the next step is, we are talking about beta. So put the OH above and then hydrogen down. At carbon atom number 6, don't interfere with it. Let it sit here quietly. Now, this one already formed hemiacetal. So what it means here is the hydrogen is still placed here. Don't interchange because the OH already formed the hemiacetal. Whatever we are doing here is you are trying to play around with carbon atom number 2, number 3, and number 4. It means twist it in clockwise direction. Say inaenda in clockwise direction. Do we say the positive side? Because reverse is always the negative side. So it goes in clockwise direction. If you twist it in clockwise direction, Glory, we have L, galactose, then what you do, put the OH inside. Because whatever was to the left will go inside the ring, and then the hydrogen which is out will be here, which is on the right will be outside the ring. At carbon atom number 3, we are drawing L. It's already to the right, so the OH will come outside, hydrogen inside. It means at carbon atom number 4, the OH is to the left. Now you put the OH above and then hydrogen down. So twisting is not confusing. Just try to note that when we are twisting, you twist in clockwise direction, the way the minute hand moves. So you'll just know that whatever was to the right will come outside. Whatever was to the left mostly goes inside or it will be up. But then if somebody talks about a beta and alpha, please don't draw linear. draw the cyclic form. After drawing the cyclic form, check first if the functional group is a ketose and if it's a pentose. You know the ketose I'm talking about, fructose. Fructose and pentoses will form a furanose, a 5-membered ring. But then aldoses are going to form a 6-membered ring, which is on the board. So the hemiacetal, whatever you can see there, up there, that cycle is a covalent bond. The OH at the 5th carbon atom and the functional group, they will be a covalent bond forming. But then, since it's an aldose, it will result into a 6-membered ring called pyranose. It means fructose will look like this. We are describing furanose and hemiketal. Then we'll be done with question number 1. So we are talking about fructose. Let's talk about D-fructose. It has to be in linear form 3, 4, 5, 6. Carbon atom number 2 has a keto group. Carbon atom number 1, CH2OH. Carbon atom number 3, OH to the left. 4, 5. Means we want to draw alpha D fructose. Just know that we are going to draw a cyclic form. Go straight and put the 5-membered ring, Then you are talking about alpha. Bring the OH down here. It means this is carbon atom number 1. This is carbon atom number 1. This is carbon atom number 2. This is carbon atom number 3, number 4, number 5. And then the 6th one will sit up here, CH2OH. Meaning, for D-fructose, at carbon atom number 3, the OH will be inside, hydrogen out. At carbon atom number 4, OH outside, hydrogen inside. That is alpha D fructose. But a hemiketal is formed there because still a covalent bond is forming. The OH at the 5th carbon atom. Is it true to say that even the mirror images can be? Of course, but you know, the mirror image, you are going to retain beta and alpha. What is going to change there is you are going to talk about beta D glucose and beta L glucose. You are not going to talk about alpha and beta, no. If it is beta, it's beta, but still the mirror image will come in the placement of the OHs. So it has to be alpha D mannose, alpha L mannose. Those are mirror images. They're stereoisomers. Yes. Phoebe, it is true. Is when you ask to draw beta, cyclic form is when you are asked to draw beta or alpha. Correct, Panay. That is correct. So when you see beta and alpha, please don't draw linear. Sometimes it makes me sad. A student has an idea, but now you've gone the wrong way. Because if I ask for beta and alpha and I already see the linear form, I give you a very big wrong. I will not even consider that you drew it and no. And then mostly if I ask, okay, so the cyclic form applies for both D and L. Eunice, don't confuse the cyclic form and the linear form. At the cyclic form, we are talking about, you have to add the word alpha or beta. So even if it is D and L, but then there has to be beta or alpha. Of course, you can draw beta L mannose, alpha D galactose. So it has to have alpha or beta. But of course, you can draw any form of them. So as long as you can play around with the OHs at the carbon atom number 2, number 4, and number 5 for the pyranoses, carbon atom number 2 and number 3 for the furanoses. It's fine. When you ask to draw beta, yes, correct. Parani has just cleared. So I've explained hemiketal, you see, the covalent bond which is forming there, OH at carbon atom number 5 with the keto group, the functional group at carbon atom number 2. You can see whatever forms there. This one is the hemiketal. But then it resolves into a 5-membered ring called furanose. That's how important it is, and that's how simple it is. We are at number 2, still Roman 1. We are saying you can draw D-galactose. So if you see D-galactose, L-mannose, very simple. You know what I need there is a linear form. My friends, the exam is very easy. Just understand the structures. We are going to pass. I told you, let nobody tell you that biochem is difficult. That is why we have the channel. We are going to simplify it. Only if somebody allows to work together so that we can simplify it. We are saying D-mannose. It has to be linear. Is it D-mannose? Let me go back again, because I want to do both of them at a go. Oh, D-galactose and L-mannose. D-galactose and L-mannose. L-mannose, D-galactose. They are both 6 carbon sugars. 1, 2, 3, 4, 5, 6. Naming of monosaccharides based on the number of carbon atoms in the main skeleton and based on the functional group. So they are both hexoses, 6 carbon atoms in the main skeleton. 1, 2, 3, 4, 5, and then the 6th one. That is met. The second criteria, based on the functional group, they are both aldoses. And I told you, you have to balance the bonds of the carbon. Looking at atomic number of 6, configuration comes to 2 to 4. So you have to maintain that because you can't put excess. Now, the last carbon atom, CH2H, we are drawing D-galactose and L-mannose. So it means there is no alpha and beta. It has to be linear. We start with mannose at carbon atom number 2. At carbon atom number 2, since it's a mirror image of the D-mannose. So 2 and 3, we will have the OH to the left. Then 4 and 5 will come. What did I say? You have the OH at 2 and 3 to the right. And then 4 and 5 will be to the left. Because the normal mannose, which is D, we have both carbon atom number 2 and number 3, the OH is to the left, and then the hydrogens will be to the right. And then at carbon atom number 4 and 5, it will always be to the right, and then hydrogens to the left. But now it is L-mannose. So it's mirror of a D. So at carbon atom number 2 and number 3, we will take our OH to the right. At carbon atom number 4 and number 5, you will take your OH to the left. And then for D-galactose, it is simple. At carbon atom number 2, you will have the OH to the right. Carbon number 3 and 4, you will have the OH to the left, and then number 5, you will have it to the right. Simple as that. We have D-galactose, and the other one is L-mannose. So the cycle, okay, Phoebe, can one draw the formation of the hemiacetal and the hemiketal? Can one draw the formation? What do you mean by the formation? The hemiacetal, what I need is, I think that one the students have seen. The hemiacetal, what I want is, I don't know whether, yeah. Since it's recorded, even if I rub, you'll be able to see after when you are revising. So I told you I have a limited space. And I also have to answer all the questions of the students. Phoebe is saying, can one draw the formation? The formation of hemiacetal. You mean the one which I was pointing at this? Or this, Phoebe? Yes? That is what you meant? Oh, can one draw the formation of hemiacetal and the hemiketal? Kindly draw. Oh, Phoebe, I said this is hemiacetal. But at some point, because it results in the formation of the 6-membered ring, so I need that cyclic, but then you have to point it there. Because if you leave it without pointing that part, then it means you don't know what you are describing. Maybe you are describing for me pyranose instead of the hemiacetal, which I need. So at that point where the covalent bond is forming, that is what I need. Because the hemiacetal and the hemiketal will result into the 6-membered ring or the 5-membered ring. So you have to point out, you have to draw it in cyclic form and point out if it's a 5-membered ring, the hemiketal, the formation of a furanose. The 6-membered ring, the hemiacetal, the formation of a pyranose. Alpha L galactose and beta L fructose. I'm going to draw all of them. I'm very patient, by the way, as I answer the students. So we are going to cover Roman 5 and 4. Alpha L galactose. So you have to draw the cyclic form. I told you when you see alpha and beta, you will know very well. Yes, Phoebe is still asking something. Let me see. Like when you combine the functional group and the carbon atom number 5, then, yes, so it's the functional group and the OH at carbon atom number 5. If it is the functional group, which is ketose, for the case of fructose and the pentoses, pentoses now, it doesn't matter because they are going to form the 5-membered ring. If you remember the ribose, which forms the furanose, ribose is an aldose. So it doesn't matter. For the pentoses, whether it's a ketose, it's a ketopentose or an aldehyde pentose, it's going to result in the formation of a furanose. But now the exception for those hexoses is on fructose. Fructose, as much as it has a keto group at carbon atom number 2, that is why it's going to result into a 5-membered ring. So the functional group and the OH at the 5th carbon atom, the functional group for the aldoses and the OH at the 5th carbon atom will result in the pyranose. Yeah. So the beta and alpha, it will tell us that we have to draw the cyclic form. So I'll start with the galactose. Let's go straight and do the 6-membered ring. Fructose, let's do the 5-membered ring. So I confirm it says alpha, L, galactose, alpha. Come straight and put the OH below at carbon atom number 1. It's the one which determines. At carbon atom number 5, already the hemiacetal. 6 will sit here quietly. But now it is L galactose. It means OH will come down here. Carbon atom number 4. Down here. Carbon atom number 3. Because you can see the OH is to the right instead of left. For the D is left. For the L it is right. That is alpha L galactose. It means for fructose, it's saying beta L. Fructose, beta above carbon atom number 1, beta L, fructose. It means at carbon atom number 3, the OH is outside. Carbon atom number 4, it will be inside. Already the hemiketal formed CH2 OH. Simple. That is alpha L galactose, clearly shows, and then we have beta L fructose. Simple as that. Remember, we are twisting it in clockwise direction. That's how important it is. But then see the functional group. Know that it will result in a 6-membered ring or a 5-membered ring. It tells for you to draw a ketotriose and a ketoexose. Ketoexose is simple. Please, when I talk about ketoexose and ketotriose, don't give me a cyclic form. Cyclic form is wrong. Because what I'm testing here is, you have to show me the linear form. You have to show me clearly where the keto group is on that structure. Is it 3-carbon sugar? Is it 6-carbon sugar? Where is the functional group? If it's keto at carbon atom number 2. So how will you show me the keto group and the number of carbon atoms if you draw it in cyclic form? So it has to be in linear form. A ketotriose and a ketotriose and a ketohexose. It means a ketotriose looks like this. I'm just telling you to draw for me a ketotriose. Simple. That is dihydroxyacetone. And then a ketohexose, just draw for me fructose. That is it. That is it. Simple as that. Ketotriose and ketohexose. You have to draw in the linear form. So don't draw it in cyclic form, please, because in that question, I'm just trying to test if you know the functional group and the number of carbon atoms, which forms as the criteria for naming of monosaccharides. Question number 3. Draw structures of sucrose, lactose, maltose, and the monosaccharide components and type of glycosidic bond present. So it means for each of those 4 marks, I told Moses, don't worry about marks. The marks will always fit questions. These are just revision questions by giving example. Especially by the time I was talking about define and draw structures, that should be already more than 2 or more than 1, because structures will take 1 mark. I would have said draw structures of. So in this case, I'm talking about structure of sucrose. Each of them will give 4 marks. So sometimes these questions, some are going to repeat themselves. So we'll be able to maybe skip because we've already discussed them. Only if somebody wants clarity, then we'll be able to understand in the chat and I'll clarify. So we use the L structures to draw the cyclic forms? No. Odero, that is not true. That is not true at all. For the L and D, the cyclic forms do not enter where the L and D are. What you have to note here is, Odero, before you understand to draw the cyclic form, we have to start with the linear form. If you don't understand the linear form, drawing cyclic will be very difficult. So we use both D and L, but then alpha and beta has to come in. It's not just D and L. And not that the other one is excluded. No, I didn't say that. We include both D and L, but then it has to be alpha or beta. So you have to start with the Fisher's projection for you to understand the Haworth projection. And I talked about the cyclic form because at the point we are drawing the disaccharides, they have to exist in cyclic form. And the cyclic form, I mentioned that it promotes solubility of those disaccharides. So we start with the D and L. You draw the linear form. Then you are asked to draw alpha L, alpha D, beta L, beta D. You'll straight away draw the cyclic form. Odero. So not necessarily that you'll use L. I was just following the question, the way I had put it there. I talked about L. Okay, that's where the confusion is. L-galactose and L-fructose. No, those are just examples. You can also use D, as long as it has alpha and beta. Odero, tell me if you still have something which is disturbing or you got it. Please tell me in the chat. If you are not clear with something, I'll let you know, or I'll explain. Madam, would you please repeat the placement of H and OH on the alpha and beta? Correct. Good. Millicent got it. Brian, I'm going to repeat that one. Now, Brian, just be keen. I'm going to repeat it when we are going to draw the structures of the disaccharides, right? Just stay where you are. I'm going to repeat that one. So as we are going to draw the sucrose, lactose, and maltose, we are going to stress much on the beta and alpha. So Brian, just take note. I'm looking for my eraser where I have put it. Just a minute. I'm looking for my rubber. Okay, I've seen it. So, Brian, just be keen. I'll be able to explain the placement of the OH. And I mentioned that the carbon atom number 1, tell us whether it is a beta or alpha. And I still mentioned that when we are drawing the disaccharides, the first monosaccharide component is the one which will control the naming of. It dictates, not control. It dictates the naming of the type of glycosidic bond. So we start with maltose. And I told you that don't just throw for me and say 2 glucose units. I'm not going to give you mark. You have to say alpha D glucose plus beta D glucose. Now, we are drawing maltose. You already know the first monosaccharide component should be an alpha D glucose. Go straight. We've learned much about them. So it's going to form the pyranose. Now, let us place our carbon atom number 6 sits there. Now, it is D glucose. It means that the OH at the 4th carbon atom will be down. At the 3rd carbon atom, it will be inside. And then at carbon atom number 2, it will be outside. Now, Brian, if you look at that structure, the OH, Paranai is saying something, D is the opposite of L. Mira, placement of OH depends whether it's an alpha or beta. Correct. Paranai, I think you are clarifying something. Brian, I want us to check the position, placement, which placement of which OHs. I'm stressing on carbon atom number 1. Or you mean placement of the OH? Yes, using the structure there, Brian. I'm trying to repeat. Let me put it. The first monosaccharide component should be alpha D. So look at that. At carbon atom number 1, the OH is below. I haven't started drawing. I'm going straight to draw the maltose. But you have to be clear, Brian. Look at the structure. So in the linear form, it was a D glucose. But now we have to add the word alpha to show that we are placing the OH below the ring at carbon atom number 1. But now, if you looked at our D-glucose, look at carbon atom number 2. This is 1, this is 2, this is 3, this is 4, this is 5, this is 6. If you look at carbon atom number 2, you know when you draw D-glucose, that OH at carbon atom number 2 will be to the right. Then, at carbon atom number 3, the OH will be to the left. Carbon atom number 4, the OH will be to the right. So it means if it is to the right and we are twisting it in clockwise direction, the OH will be outside the ring. Then at carbon atom number 3, it will be inside because it was at the left. Then at carbon atom number 4, you can see the same position as carbon atom number 2. So whatever we are doing here is, since the OH is below, do you know that is why maltose, the type of glycosidic bond, starts with an alpha? Because at carbon atom number 1, it will attach itself with the carbon atom number 4 of beta D glucose. It is still D glucose. Nothing is changing. Beta D glucose. Beta above. Imagine. That's how simple it is. We have an alpha 1,4 glycosidic bond. The name of the glycosidic bond comes from the first monosaccharide component, which is an alpha D glucose. It will dictate how the day will end there on that maltose, how the glycosidic bond is going to form. So since the OH is below the ring at carbon atom number 1, it is easier to extend it downwards as it connects to the carbon atom number 4 of beta D glucose. And for that matter, you see that OH. Yeah, Majid, I'll explain. Glucose not phase. Oh, now you can see, I think. You look for that matter, you can see the OH above at the second glucose. That is why it is a reducing sugar. You've already done the test in the lab. Only the BMLS app haven't done. You do the Benedict test. And the Benedict reagents, presence of the copper sulfate, it is blue in color. You add any of those samples you've given, the sugars, then you see the color changing. For maltose, it is going to change as much as a disaccharide. You can see the presence of the OH on beta D glucose will make it to change color. Yes? So the first monosaccharide component will control the name of the glycosidic bond. It is alpha because the OH below the ring, you connect to the 4th carbon atom of the beta. That is maltose. So we have to understand the cyclic form because our disaccharides, they can't be drawn in a linear form. Why should they be drawn in a linear form? And yet we are talking about the cyclic form promoting solubility. So it increases solubility of those disaccharides. We are talking about lactose, the milk sugar, how it merges well when you prepare tea. Fresh milk. You talk about sucrose, the table sugar. You can even stir it in cold water and it still dissolves. So we are talking about promoting solubility, the cyclic form. Lactose. I'm drawing lactose. If you look at lactose, we are talking about the first monosaccharide component should be a beta D galactose plus a beta D glucose. You have to mention it the way it is. And it is going to form a beta 1,4 glycosidic bond. Meaning, let us draw our beta D galactose. Beta. That is galactose. It means the beta is above at carbon atom number 1. But since it is D-galactose, go straight to carbon atom number 4. The OH will be above. Carbon atom number 3, the same position as number 4. It means number 2 will be down here. Number 5 and number 6 don't interfere with anything. That is beta D-galactose. Imagine if this one is not beta, I give you a wrong. I always check this one more than anything else. If the first monosaccharide component is not a galactose, everything is already wrong. Now it is a beta. It means that it is easier to extend up, down, then up, then do this. Then you have your beta D-glucose, beta D-glucose, then you talk about a beta 1,4, carbon atom number 1, carbon atom number 4. Still, lactose is a reducing disaccharide. The presence of the OH there tells much about it. Let me try to focus it well so that Majid can see. Tells much about it. Some books, even the one which I projected for my upgrading students, it is still the same story, but it was taking this up here because it will go up. It was showing something like this. I know I'm not good in drawing, but I can get it right. That was the galactose. Glucose, sorry. So it was going up. Either way, but it has to show that the first one will tell much about the type of glycosidic bond which is forming. If it's above, we talk about beta. If it's below, we'll talk about alpha. Then sucrose, being the last one, looks like this. For sucrose, you will have alpha D glucose, beta D fructose. So some books will draw it like this. The first one will have to be this. You know, it's an alpha, meaning OH is below. Then the bond will come straight and you'll have something like this for some books. For some books, you'll have something like this. At carbon atom number 3, at carbon atom number 4, at carbon atom number 5, and number 6 sits here. At carbon atom number 2, at carbon atom number 3, number 4, number 5, and number 6. Some books, it will show an alpha 1,2 glycosidic bond for some books. For my student in class, I didn't give that one. I'm going to give my version. But I want to explain the point there. You can see that is why sucrose is a non-reducing sugar. All the monosaccharide components are involved in bonding. There is no free carbon there. There's no free OH. And for that reason, sucrose is a non-reducing sugar. 1, 2, the 2 means the second carbon where the keto group is. 1, 2 alpha Because the first monosaccharide component was an alpha. Alpha 1,2 glycosidic bond. I'm going to draw the one which I drew in class for the BCHD students. But it still applies the same. If you're fine with that one, because if you read a lot of biochemistry books, they will give you different versions. But as long as the concept is the same, it is involved in bonding. It's already at carbon atom number 1 up there on the alpha D glucose, and then you have it at carbon atom number 2 where the keto group is on fructose. So in that case, you don't see any OH hanging there. All the monosaccharide components have been involved in bonding. So in that case, sucrose is a reducing sugar. Let me draw the version for the students, which was in class. Still the same. Whichever is easier for you, my dear. As long as I can understand the structure is correct, don't mind. As long as you draw for me a correct structure, I don't have an issue. So the one in class was going like this. The one in class was going like this. That is also allowed. I didn't say that you don't draw it like that. But you see, the absence of oxygen tells a lot that it is a non-reducing sugar. CH2OH. Here. So this is another version of drawing sucrose. But the main point here is it is a non-reducing sugar because all the monosaccharide components of that disaccharide have been involved in bonding. So in that case, it doesn't reduce the Benedict solution from blue to brick red. Question number 4. If somebody don't have question, I'm going to address as we proceed. We are talking about writing short notes on similarity and difference between cellulose and amylose. You could remember they were homopolysaccharides. In this case, for my BCHD students and the regular students, we did not do heteropolysaccharides. Neither did we do sugars amines. I said that when the groups are mixed, if it's not only one group, then it becomes a bit tedious for the BCHD group. For the BMLS, if they are alone, I could have taught the heteropolysaccharide, but maybe we can accommodate it next time. So I didn't do sugar, amines of the sugars as I did for the upgrading. So you'll just excuse us, not that I forgot, but then I was covering only what I need to cover in their content. So I did do heteropolysaccharides, but I did homopolysaccharides. I also didn't do the amines of sugars, but I still think they're very important. Maybe we can accommodate them in their curriculum later on. So we are talking about write short notes on similarity and difference between cellulose and amylose. That's how simple it is. Because if you could remember, they were homopolysaccharides. On hydrolysis, you said sucrose is a non-reducing sugar. Phoebe, sucrose is a non-reducing sugar. You can see the H there, no oxygen. It doesn't reduce. For the practicals which you did in the lab, there is one, however much it was not labeled, there is this sugar which did not change. Yes, correct. Nura has answered. Thank you for that. So we are talking about the polysaccharides. On hydrolysis, they will just give glucose. Thank you for that. On hydrolysis, the homopolysaccharides will only give us glucose. And the best examples we had were glycogen, we had starch, we had cellulose, and even some we didn't discuss much, but we had the three core ones which we discussed. And at that point, whatever you could mention clearly here is, if you look at cellulose and amylose, the difference here is cellulose has beta D glucose, cellulose. Amylose has alpha D glucose. Look at how important it is to learn the linear form, which translates to cyclic, because when you talk about the polysaccharides and the disaccharides, now you are talking another term now, the alphas and beta. So if you look at cellulose, it is linear. Amylose is linear as well. That is similarity. So each one of them, if you mention, I'll give a tick. But I still told Moses, don't worry about the marks. Let's get the concept first. So cellulose, the difference between cellulose and amylose, you know, cellulose is found on wood, which is still plant. Amylose is also found in plants. But then the big difference here is cellulose has a beta D glucose, forming a beta 1,4 glycosidic bond. Amylose has alpha D glucose, forming an alpha 1,4 glycosidic bond. Simple. Don't complicate life. Question number 5. Similarity and difference between glycogen and amylopectin. That is now where it comes. Storage form of glucose in animals is glycogen. Storage form of glucose in plants is amylopectin. But another difference is amylopectin is less branched than glycogen. In other words, glycogen is more branched than amylopectin. But now they have a similarity. They are both branched. It means that they have both alpha 1,4 and 1,6 glycosidic bond. They are both branched. I'm going to skip question number 6 because we've done it. Because I don't want to repeat a lot of things which we have done. Because people are already getting exhausted and we haven't done amino acid, which I have to mention, using the peptide bonds. So question number 6 is similar. Alpha D glucose beta, you can draw. I just want you to draw, nothing to say much. And then epimers and functional isomers, we've covered that. Mwalimu, where are the numbers coming from when you talk about the glycosidic bond? Oh, good. Hamisi. So Miss Mohammed, if we talk about 1,4, or on the board, we talk about 1,2. So the first carbon, the first carbon of the first monosaccharide component, the fourth carbon of the second monosaccharide component, that one I'm talking about, lactose and maltose, what you saw there. When you talk about sucrose, which is on the board, the first carbon, that is where the one comes from. The second carbon, which we are talking much about on fructose, it brings clearly that the keto group, because the keto group is carbon atom number 2. So the numbers will come from where, the position where the glycosidic bond is forming in the 2 monosaccharide component. Repeat 5. Okay. I was saying, Moses has requested, repeat 5, that we get similarity and differences. Similarity and difference between glycogen and amylopectin. Thank you. Amisi, thank you. So we are saying that structurally, if you look at glycogen and amylopectin, let's start with the difference. The difference in glycogen and amylopectin, storage form of glucose in plants is amylopectin. Then, storage form of glucose in animals is glycogen. That is difference. Another difference is, we said, glycogen is more branched than amylopectin. And we mentioned in class that for glycogen, you'll go 8 to 10 glucose units, then you get a branching point. 8 to 10, you get a branching point. But then, contrary to amylopectin, you'll go 20 to 30. So it shows amylopectin is less branched than glycogen. Similarity, they are both branched. It means they both have alpha 1,4 and alpha 1,2, alpha 1,4 and alpha 1,6, glycosidic bond. Moses, was that clear? So we are skipping question number 6. We've done a lot. Similarity and difference between alpha L and beta L. Just draw the structure. Don't explain anything. I'll be able to see and give a mark. Draw 2 structures in each case to define between epimers and functional isomers. We've done that one, please. So some, which we've covered, we are just going to mention as we pass. Define epimers and give structures of 2 why did I repeat it so much? I think I was just collecting questions from different ends. So it might be a repeat, which is not a repeat per se, but we are almost starting on amino acids. So it defined pyranosis and furanosis and give structural. That one we've done in length. You'll allow me to start on the amino acids. Draw a tetrapeptide. And I told you people, I'm not going to set for you to draw for me an amino acid. If it's not section C, where you can play around with 1-letter code, 3-letter code, I told you can use your names. If a letter is missing in your name of the 20 amino acid, just use the ones which are available. So we are starting with Davy, men first. We are starting with Davy, and we said in class, Davy is a tetrapeptide. Davy, 4 amino acids are involved there. Yes. So I told you, don't be in a hurry. If I ask you a question like this one has to be 5 marks. The reason why it is 5 marks, I want you to draw for me D. What D is? Draw for me A. Draw for me V. Draw for me I. Please. I'm going to give you a mark for each one of them. But if you go straight and draw the tetrapeptide, you might get one wrong, which you didn't get right. Then you'll get everything 0. But in this case, if you missed one, you'll still get 3 marks. So D is aspartate. Start. I said the amino acids, there is carboxyl terminal end and amino end. If you can't remember NH3+, please give me NH2. Aspartate, acidic amino acid. Do CH2, COOH. Alanine will follow, which is aliphatic. Alanine will follow. It is aliphatic. Simple. Valine will come next, aliphatic, but then branched chain. I'll be able to put it well so that you can see at the end. Valine. It is branched. It is branched, yes. But it also falls under aliphatic. And even our leucine, isoleucine, it's also aliphatic. But it is branched. At a certain point, it is branched. It is branched. Yes. Look at that. A tetrapeptide. We are drawing Davy. We are going by the name, Davy. Could you please redo the beta D fructose and try numbering the carbons? Yes, I'll do it, but let me do the amino acid, then I'll do Moses. Just remind me before I forget. I'm trying to project the Davy. Yes. Look at that. That one you will score. You will score 4 marks. Bila kupinga. Then, what happens at the time a peptide bond is forming? water is released, H from the other side. Carboxyl terminal end of aspartate, amino terminal end, they combine. At that point, water is released, the first water. Carboxyl terminal end of valine, amino terminal end of, no, carboxyl terminal end of alanine, amino terminal end of valine. Carboxyl terminal end of valine, amino terminal end of isoleucine. You can see the three places where water is released. So put plus 3 water molecules. Now, let's draw the peptide bond. We start with this side. We start with that side. We said carboxyl terminal end of aspartate, amino terminal end of alanine. Then put alanine, carboxyl terminal end, amino terminal end, then put leucine. Valine, sorry, not leucine, valine. Even leucine is not there. We have isoleucine. Carboxyl terminal end of valine, amino terminal end of isoleucine. Then finish by having the isoleucine. Simple as that. Simple as that. This is the peptide bond. At that point where the carboxyl terminal end and the amino terminal end of the amino acids residue, pardon, look at that. Carboxyl terminal end of aspartate, amino terminal end of alanine, carboxyl terminal end of alanine, amino terminal end of valine, carboxyl terminal end of valine, amino terminal end of isoleucine. Look at that. You'll scoop all the 5 marks. Odero, I talked about it's a tetrapeptide. 4 amino acids are involved. We said the name of the peptide comes as a result of the number of amino acids which are involved in bonding, not the number of peptide bonds which are forming. The number of amino acid residues involved in the formation of the bond. That is where the names come from. So if it's a polymer of amino acids of which you can't count, then you are forming the proteins. And you can't talk about the proteins without the amino acids. And the amino acids will not make the protein without a peptide bond. And even you saw at the primary structure of those proteins, we have the disulfide bonds together with the peptide bonds. So it's a linear form. Yes? My phone is almost, it's a bit low in battery, but I hope it will be able to take us through, because I want to do much on the amino acids, but I want you people to agree with me if we can revise again on Wednesday before we can do the cut, because I can see I can finish until number 14, and then the essays we finish on Wednesday, because we have to sacrifice our time. Can I see the response, Tabitha? The class rep BMLS. I don't like putting too much things on the head of the students. I don't like. So I request, and people will agree with me, we do until number 14, and then by Wednesday, the group come back again. We do essays, then you'll be able to be ready for the card. Can I see the response? Yes, we do it on Wednesday, correct, because I don't like pumping too much. My phone is already at 5%. So, okay, Herbert. Can you see something? Because from my end is a bit dim. I want to do the Agnes, or we can stop. Let us stop at number 10. Then we can swallow whatever we have discussed so far. We go and digest. Is it fine? It's not like the world is ending tomorrow. It's not ending tomorrow. Let us go and swallow until where we've done Devi. Then I'll come on Wednesday. We start from number 11 and we finish with the essays. Is it okay? Yes. Wow, Raji. Hi. Or somebody, Moses. I can finish by answering Moses' question. Moses, can you type whatever you said, and then I can finish with that so that people can go and relax. Tomorrow is Sunday, so you can prepare. But then let's have it on Wednesday again. Class rep, wherever you people will be, I think we can log in anywhere. Whether you are on holidays or on trip, you just log in onto your phone and you hear what Madam has to revise, because we have to finish with the revision. Moses, you said what was confusing? Was it fructose? L? Moses, just type it, then I can discuss it, and then I leave the students to go. You said something about L-fructose, I think. So let me draw L-fructose. I can't remember what you said, but Moses, I'm drawing L-fructose, sorry. You said something, and I can't remember. Because some chats have come after whatever you asked, so it has passed. 1, 2, 3, 4, 5, 6. You said something, Moses. I want you to type. Oh, Moses didn't hear. Okay, guys, thank you so much for the time. Kindly, you can have a good night, and let us meet on Wednesday. Let us sacrifice our time only for these few weeks, and then you'll be happy, enjoying Christmas holidays, knowing that you give it all, and it will pay you back. So all the best. Madam loves you all, and thank you so much. This far, it is you people. I appreciate all my students who have been teaching, even before I could start the channel. They are still very supportive. They'll come and subscribe. They'll come and get something. They'll even advise people to. So I say thank you. So bye and have a good night, and God bless.